The first paper that we are going to have in that group is submitted by India, and we are really happy that we have from the colleagues from BITS Pilani with us in this paper in the conference. And the paper is entitled Multi-Objective Optimization of Machining Parameters to Minimize Surface Roughness and Power Consumption using TOPSIS. We're looking to the presentation of this paper.
Hello everyone, I am Pawanr from Department of Mechanical Engineering, Birla Institute of Technology and Science, Pilani, India. First of all, I would like to thank 7th CIRP Global Web Conference Organizing Committee for selecting our paper for the presentation. The title of my presentation is Multi-Objective Optimization of Machining Parameters to Minimize Surface Roughness and Power Consumption using TOPSIS. The content of my presentation are Introduction, Methodology, Experimental Planning, Result and Discussion, and finally concluding remarks. This is the world energy consumption scenario which is presented in a pie chart which is having the 4 major sectors: commercial, residential, transportation and industrial, in which commercial sector is accounts for 13%, residential 16%, transportation 21%, and the major energy consumer is the industrial sector, which is 50%. If we explore industrial sector, then we find that the manufacturing is accounts for 37% of energy consumption, and mining, construction and others 63%. In manufacturing sector, the key energy consumer is the machine tools, which accounts almost 75% of the total energy consumption. So indirectly we can say that the machine tools are the significant energy consumer of the world's total energy consumption. This is the pie chart which is representing the energy consumption regarding the country India in major sectors. The domestic sector is account 24%, agriculture 18%, commercial 9%, and others 9%. And in case of India, industrial sector is also a major energy consumer, which accounts almost 40% of energy consumption. Also, the energy consumption in India is the third largest after China and USA. So the 37% of global energy demand is arises due to the manufacturing operations, and the machine tools are the key energy consumer in the manufacturing sectors, and the energy efficiency of the machine tools are very less, which is around 30% only, and more than 99% of the environmental impacts are due to the electrical energy consumption of machine tools during the discrete part manufacturing process like turning and milling. Also, the machine tools manufacturing industry is globally accounts for 68.6 billion, which is a very huge amount, and very less assessment has been conducted for discrete manufacturing facilities. And also the power consumption up to 6 to 40% can be reduced, means there is a potential for reduction of power consumption by selecting of optimum cutting parameters, tools, and optimum tool path design. So considering these facts in the present study, we have conducted the multi-objective optimization for 2 responses. One is power consumption and another one is the surface roughness, because surface roughness is also a widely accepted product quality index in the industry, and the multi-objective optimization has been done by using TOPSIS method. The methodology followed in the present study is shown here, in which in very first we have to select the machine tools, then the machining parameters and the process characteristics. In the present case, we have select the machining parameter cutting speed, depth of cut, and feed rate, and process characteristics are the surface roughness and power consumption. Then we have to plan the experiment. In the present case, we have planned the experiment using the L27 full orthogonal array, and then once we have conducted the measurement, then multi-objective optimization has been performed, and once we get the optimal results using the present optimization technique, then we have to compare with the existing literature, and then finally make the concluding remarks. In the present study, we have conducted the experiment on the heavy-duty HMT central lathe machine, which has the maximum spindle speed is 2300 rpm, and the spindle motor power rating is 5.5 kilowatt. The workpiece material which was machined is mild steel of grade A ISI 1045, and the cutting tools is used as a carbide cutting inserts in the tool holder. This is the systematic representation of cutting force measurement setup, which comprises a workpiece is held in the chuck, and there is a cutting tool which is held in the tool post, and the tool post is resting on the dynamometer, which is a crystal dynamometer in the present case, and the dynamometer is connected to the amplifier, and finally amplifier is connected to the computer, and in which we have the dynamometer software, and we get the readings. In the present study, we measure the power consumption indirectly. Means in very first we have to measure the cutting force, and the cutting force is multiplied by the respective cutting speed, and we got the particular power consumption for the cutting operation. And this is the actual representation, is actual picture of the setup, in which the crystal dynamometer is clearly visible, on which the tool post is resting, and in the tool post there is a tool holder, and the cutting inserts are holded on the tool holder, and this is the component which was machined, and this is the one of the reading taken during the experiments of the cutting process. This setup is for the measurement of surface roughness. In the present study, we measure the surface roughness using Taylor and Hobson makeup profilometer, and we measure the surface roughness at really equal position of the machine component to get the overall surface roughness readings of the machine parts. And in the computer, you can see one of the reading, and this is the zoom view of this reading, and finally the average value of these peaks and valleys is considered as a surface roughness of the machine. So this is the finally experimental measured values of the surface roughness and power consumption. Total 27 experiment has been conducted, which is based on the L27 full orthogonal array for the different combination of the cutting speed, feed rate, and depth of cut, and these are the respective surface roughness and power consumption readings. So once we get the results, means measured values of the surface roughness, power consumption for different combination of the input parameters, we use TOPSIS, which is known as the technique for order preference by similarity to ideal solution, as an optimization technique, which converted these two responses, surface roughness and power consumption, into a single index. And the detailed information about the TOPSIS has been presented in the article. In brief, TOPSIS measured the elusive distance from the ideal positive solution and ideal negative solution, so which is known as the separation measures. In the table you can see that the SPM plus M is the positive separation measure, and the SPM minus is the negative separation measure, and finally using these two separation measures we have to calculate the closeness coefficient, which is represent the combined performance index for these two responses, and finally this closeness coefficient is used as a single objective, and then we have calculated the SN ratio using the Taguchi method. So this is the main effect plot for SN ratio, which is prepared in the Mingitech 2018 software, and according to the Taguchi, the highest SN ratio for the level of a particular input process parameter is representing the optimal level of that particular parameter. So in case of cutting speed, the level 1, which is 103.31 meters per minute, having the highest SN ratio. So this is the optimal level of the cutting speed, and similarly in case of feed, the 0.12 mm per revolution is having the highest SN ratio, and in case of depth of cut, the 0.5 is having the highest ratio. So according to the TOPSIS and Taguchi SN ratio, we can say that the optimal cutting levels according to the present study is V1, F1, and D1. So here we represent the comparative analysis with the existing literature. Previously on the same experimental data, GRA, Gray Rational Analysis Optimization Multi-Optimization technique had been applied, and they got the optimal cutting levels of V2, F1, and D1, means level 2 of the cutting speed, level 1 for the feed and depth of cut. But in the present case, using TOPSIS, we got the different optimal cutting parameters. So we have to just compare the values of the responses on the optimum cutting parameters, and we found that the relative percent change in the response at TOPSIS over GRA, that power consumption is improved by 30.41%. Means by using the present optimal cutting levels, we minimize the power consumption by 13.41%, but at the same time the surface roughness was deteriorated by 48.52%. And this type of trends also seen in the literature. Means UI and Chakrudar had optimized the cutting parameters using these two methods, TOPSIS and GRA, and they had also found the different optimum levels for the each optimization technique. Last, the concluding remarks. The turning experiments based on the L27 full factorial orthogonal array were conducted on mild steel AS7045 using the carbine inserts. The multi-optimization has been done for two process performance characteristics, power consumption and surface roughness, using the TOPSIS with the Gucci method. And the optimal machining parameters were found: cutting speed 103.31 meters per minute, feed rate 0.12 mm per revolution, and depth of cut 0.5 mm. And when we compare the present result with the previous optimized result, then we found that an improvement of 30.41% in power consumption, and at the same time there is a deterioration of 14.52% for the surface roughness. So the result shows that the different optimization approach provide dissimilar results for the same experimental data. Therefore, confirmation experiments are necessary to validate the optimization approaches. So thank you very much for listening my presentation, and once again thanks to the 7th CIRP Global World Conference Organizing Committee. Thank you very much.
Thank you very much to the colleagues from BITS Pilani for the presentation and for the paper. We are now happy that we have established a connection to the authors. It's Shailendra Pawanr who is going to join us live on the stream here. Hello, Shailendra, can you hear us?
Yeah, I can hear you.
So welcome to India from Berlin. It's nice to have you here in the stream.
Nice to meet you.
Thank you. So thanks for sending the paper and thanks for doing the presentation. It's a nice paper, though. The question that also the reviewers announced during the paper process was about the criterion to use the power as a criterion for optimization. So what was the reason for you to use the power?
As concerned to the power means there is a lot of environmental issues arising in the global world. So that's why if we reduce the power consumption for a particular machining process, then it will help to reduce the carbon content, means the emission of carbon emission and something like we can reduce the environmental impacts. So that's why I am considering the power consumption. But if we see only the one part of that machining operation, then we can find there is another responses also come in action, like surface roughness.
Okay, but what about the difference to the energy consumption? So how would you distinguish between the power consumption and the energy consumption? What would you think would be the more important part to go for?
Power consumption and energy consumption can be used synonyms, because we just if we multiply with the time, if we look in a particular time, then it comes from the energy consumption. So there is no difference between power consumption and energy consumption. For particular section, we have used the power consumption.
Okay, thank you. So the second question goes towards the optimization strategy that you use. You are interested in trading power consumption for roughness. Can you comment on the motivation that you had for doing that?
Because since if we want to superior surface finish, then it increases the power consumption exponentially. So that's why unnecessarily there is a lot of huge amount of power will consumed during machining. So we just want to trade off between these two parameters. Means we have to minimize the power consumption. At the same time, we want to get the good surface finish. So that's why we are using these two responses: power consumption and surface roughness.
Okay, so do you think you could do that optimization online one day?
Yes. Pardon?
So do you think you can do the optimization, so you trade power consumption versus roughness? Do you think you can do that online during the process then?
Yeah, okay. We can also consider different parameters also from the different considered parameter, we can consider it and we can perform on the optimization, number of parameters. No problem.
Okay. Would you like to share some more insights about the context of the project and the research that you have presented? What is around the paper that you have submitted to our conference this time?
Okay, because in the present study means the power consumption not only the one of the environmental issue, but also apart from the environmental issues in the industry, there is a cost is a major issue. So that's why we are also we targeting power consumption, and we especially working on the energy consumption study of machine tools, and also we are also working on the energy efficiency of machine tools. So in the next future work, we also included some energy efficiency aspect of the machine tools.
Okay, thanks for sharing these insights with us.
Okay.
We are Shailendra Pawanr from BITS Pilani in India. Thanks for taking the time to connect with us and enjoy the conference. Thank you. Goodbye.
Oh, thank you very much. Thank you very much. Okay.
So this was the presentation of the paper entitled Multi-Objective Optimization of Machining Parameters to Minimize Surface Roughness and Power Consumption using TOPSIS. It is authored by Shailendra Pawanr, Girish Kant Garg and Srikanta Rudroy. All of them are affiliated to BITS Pilani in India.